Okay, so we will carry on with this the study that we have been undergoing at present. So, if you see this the earlier slide that I have shown you is that temperature, pressure and the characteristics of the waste. So, this one is Kr essentially also depends on temperature, pressure, characteristics of the waste and various other things also, and sometimes so it cannot be so simply examined like that, but nonetheless this one is this particular function, that is this particular function given is generally suitable for almost all various kind of situations and for all kind of problems that we will see in our exams or anywhere. We would mostly use this equation if unless otherwise told. Okay. In case if it is some other things are given, in such cases we have to find out that way only. Okay, but before we go into this, there are few things that I would like you to see. What is the value of how this, what are the likely values of Kr? What are the likely values of Kr? How Kr essentially is the value of Kr one can experimentally, what would be the value of Kr? Say this type of water body, range of Kr. Remember the same way that we have seen in the case of K or in the case of Kd, this is essentially a time inverse function. This is day inverse or hour inverse or sometimes say any other parameters like this, hour inverse like this, this is the range that we generally observe for that, and at 20 degrees centigrade. So, the adjustment, the typical adjustment that we have done in the case of fixed water body, that also has to be done here if it is given for a different temperature, right. You remember that function that I have given, that k theta is equal to k20 into theta into another function T minus 20, that is temperature 35 minus 2015. So, that value has to be given, theta is 1.047 that we explained. So, that function has to be in place. So, at any temperature adjustments is necessary. So, remember this, temperature adjustment has to be is necessary. So, here you can see the small ponds and backwaters. The backwaters is essentially where the sea enters the land and there is very little flow in the water body, there is little flow in the water body, and the water does not generally remain still. Say in a small pond also there are some waves that you see generally in the pond. So, this kind of under this kind of situation, when the water flow is very small water flow, we can see that the value is 0.23. This is the value for sluggish streams. And large lakes. Sluggish streams, having a very little speed, say about say 1 kilometer or 2 kilometer per hour, kind of say 1 to 2 kilometer per hour velocity streams, and large lakes. So, you can see the value is about 0.23 to 0.35. Large streams of low velocity, large streams of low velocity 0.35 to 0.46, large streams of low velocity, large streams of normal velocity. Normal velocity of water in most cases would be about say 10 to 20 kilometer per hour. Large streams of normal velocity, here we can see that 0.46 and 0.69. You can see the swift streams, particularly that generally comes out of the mountains. Across, is the first one is these large streams here we have discussed. These are only mostly in the plain. So this is mostly in the plain. You can see the plain, they are in the plain area. Wherever is the mountainous region, the swift streams that we generally see 0.69 to 1.15, and rapids, waterfalls. Waterfalls and cataracts. Cataracts, where the generally the water comes out, drops from a particular height. See, those of you who have seen, mostly in India, most of the cases we do not see waterfalls a lot, we see mostly the cataracts. So this cataracts are 0, this is mostly 1.15. These are the values that would be generally useful for you in the KR, unless otherwise said, depending on the type of the problems given, you have to understand, you have to find out the value of, say, mostly the large streams of swift streams. Generally for our cases we would be discussing mostly these two kind of streams of velocity, and also sluggish streams here, sluggish streams as well. So we can see these three, mostly what you have to understand and remember. Okay, this is about the water body, having the KR, range of KR, that is, this reaeration rate coefficient KR, that we generally observe like this here. Okay, and another important thing is DO saturated. The value of DO saturated is also of great importance for us. Is a DO at 1 atmospheric pressure. 1 atmospheric pressure means what? It is open. Alright, nothing else. It means, it is what DOS at open, it is an open stream. So here it is temperature. If you see the temperature at degree centigrade, this is salinity. The salinity is 0 to 5,000, this is 10,000, and this is, so this salinity is in milligrams per liter. If you just observe this milligrams per liter, understandably at 0 degree centigrade and 0 chloride concentration, we find the maximum value of oxygen, dissolved oxygen in water, the saturated dissolved value of oxygen. This is the maximum that you can see. And here, as you can further go on, you see this 13.73, 12.89, and this is 12.10. This is at 5 degrees centigrade, this is 12.77, 12.02, 11.32, and 10.66. Fifteen is 10.08, 9.54, 9.54, 9.03, 8.54, 20, 25, 30. See, this is 20, 25, 30 is 10 point, say the 20 is 9.09, 8.26, 7.56, right. You can see this, this one is 8.62, 7.85, 7.19, 7.19, 8.17, 7.46, 6.85, 6.85, 7.75 is this value, 7.08, 6.51. One thing you can very well see with temperature, with this temperature, you can see the rate of change also differs. See here it is about say 1.5 degrees, 1.5, you know, the milligram per liter change is there, wherever here it is almost about 0.3. So, as such, you know, the depletion increases with temperature and the rate of depletion decreases. Oxygen getting depleted with higher temperature, and but the rate of depletion decreases with higher temperature. Increase, yeah, increasing the pressure would increase the solubility, essentially, always, in all cases, essentially increase the solubility, right. So, here as you can see, this is the highest value that we get, this is absolutely the lowest value under this case. Say, you know, here if you can further extrapolate this, say here it would be 7 point, say 7.3, this in is, you know, 7.3 that you can see here, it is about 6 point something, you know, 6 point say 7.8, say then it is say 6 point, this one is 6 point, say 6.78, from 6.78 it would be about say 40, is about 3.38, so like that's or this is about 6.10, something like this. So, you can see this is, you know, this is the value that we generally obtain here. So, just to understand one thing, you know, this is what I have all been kept saying also, that is where the rate matters. The rate here says that the temperature with higher temperature, the this solubility decreases essentially, but the rate of decrease of the solubility essentially this is, you know, the decreases. Rate of decrease of solubility decreases, but the deficit increases, isn't it? Deficit essentially increases with temperature. So, this two things, this particular plot, this particular table would be of great importance, because in many cases, in many situations you would require this. About coming into this DOS, you know, here in this case, they say, you know, what is the deficit, initial deficit, we generally say a term initial deficit. This initial deficit or initial deficit D0 is essentially DOS minus dissolved oxygen QW dW, dissolved oxygen DOW plus QR DOR divided by QW plus QR. See that at that point of time, this is DO, DOW, DOR is equal to dissolved oxygen dissolved oxygen in the waste and the river or the stream. We write it as river or stream, whatever, river or stream. Dissolved oxygen in the wastewater and river. Dissolved oxygen in the wastewater and the river just before the mixture. Just before the mixture. Similarly, QW and QR, I have said that volumetric flow rate. It's a typical mass balance equation. It's a basically typical mass balance equation, mostly in all cases volumetric flow rate of wastewater and the river or stream. All right. Now here what is generally, or you can see, is DOS is equal to DOM. DOM, this is DOM is dissolved oxygen at the point of mixing, and this D0 is D0, remember this D0, don't confuse with DO, this is D0, this is D0 is initial oxygen deficit. This initial oxygen deficit. Why this initial oxygen? Where you have brought in this initial oxygen deficit? Where you have brought in the initial oxygen deficit is to be understood now. The reason is the reason is that initial oxygen deficit, the deficit, the term deficit through the time and distance in the stream from the point of mixture would essentially depend on the initial oxygen deficit and the BOD, this BOD of the mix wastewater and BOD of the wastewater and the water, the river water itself combined, and also depend on the rate of change. I mean, let me tell you this. So here you can see this, that if you can see the deficit D, this deficit D is a function of DO, is a function of DO, is a function of KR, is a function of KR, and also, as I have said, that function of KR that you already know, and also that there's the proportion that it has, that is the BOD at the point of mixture, BOD at the point of mixture, BOD at the point of mixture, BOD at the point of mixing, at the point of mixing, or BOD of the mixture at the point of mixing, right. So this is why these things are necessary to be found out. So we have says this is, we understand now at this point of time that deoxygenation and reaeration, are two competing processes. Two competing processes. That is, when one is on the increase, other is on the decrease. When one is on the decrease and the other is on the decrease, and vice versa. So, so we can see now that from this we can find out, we can rate of, remember in some books it is written as, even in the book by masters it is written as the rate of increase of the deficit. The word should be rate of change, rate of change of the deficit. Rate of change of the deficit. It is not necessarily that it should be always increasing or it would be always decreasing. So, here we should write rate of change of the deficit. Rate of change of the deficit is rate of deoxygenation minus rate of reaeration. Rate of reaeration. Okay. The rate of reaeration, rate of deoxygenation and rate of deaeration. Remember again, as I have said, this is the, as you can see, if it is, when it is rate of deoxygenation is higher than the rate of reaeration, it would be this would be positive, this would be negative. On the other hand, it would be negative. So, if you can leave at this point of time, you can understand this as a function. We should not be interested in which one is higher at this point of time. We would just try to see the difference. Difference is important for us than the absolute value of h. In such cases, we can write a typical function where it is the rate of change of deficit. This is dd by dt is equal to kd into L0 into e to the power minus kd into t minus kr into d. Okay, minus kr into d. The approximate solution, the approximate solution was first given by Phelps, Streeter and Phelps in 1925, and is known as, Phillips was given by Streeter and Phelps and is known universally as Streeter-Phelps oxygen sag equation. Streeter-Phelps oxygen sag equation, right? And this is the approximate solution was given and is known as this. This is what is the solution is what Streeter-Phelps, an approximate solution that it gave is kd into L0 divided by kr into kd, kr into kd, e to the power minus kd into t minus e to the power minus kr into t, kr into t plus t0 e to the power minus kr into t, kr into t. Remember this, here this is the typical approximate solution of this differential equation, an approximate solution of this differential equation, and considering that this d is a function of d0, initial deficit, is a function of L0, is a function of L0 and Kr obviously Kr that we have seen. Okay. So, considering this, this is an approximate solution that we generally get in case of Kr and Kd, when condition is Kr is not equal to Kd. When Kr is equal to Kd, when Kr is equal to Kd, we find another solution for this, which should be written as Kd into L0 into T plus D0 e to the power minus Kd into T. Okay. This is what when Kr is equal to Kd, we find a different solution. So, you can see this in such cases like this, but mostly we would see that these two are essentially different things. So, Kr and Kd not being same would be the case when we mostly consider them. And having said this, we can find out that if we just generally write x as if x is the distance downstream, xx is the distance downstream, u is the speed of the stream, speed of the stream, and t is the time from the point of mixing, t is the time from the point of mixing to a distance x, then we can this equation is just can be simply modified as Kr into Kd. This one does not change much, but here it changes a little bit. T is essentially x by u. X by u is x by u minus e to the power minus Kr x by u. Sorry, u, only u. Don't write mu. Sorry, it is only u, and plus d0 e to the power minus Kr into x by u, Okay. This is the function. This is the function that we generally observe. This is what is known as Streeter-Phelps function. Converted form that we have said. Initially this is the basic function. We have merely made a simple change in the function, considering that x and u are x, u and t are related. Considering x, u and t are related, so we have made a simple change here. So if you just can find out now, if it is for that when this the deficit would be maximum, when the deficit would be maximum can be found out from d is equal to and d is to 0. Equating this to 0, you can find out this function. We can find out the time. What is the time? We can find out the time, and if we can find out the time, we can also find out the distance. Okay. So this is you should try it yourself. It's very simple. You will generally obtain the value very easily. So in such cases, a simple solution of that is basically we generally T critical that is T critical is the time solution is a time at which the deficit is maximum, the deficit is maximum, or the concentration of the oxygen in the stream minimum is known as, is generally can be found out by, generally can be found out like this. This Tc would be, this is called as time, critical time, generally also known as this as critical time, also known as critical time. This Tc is nothing but 1 minus Kr into Kd log Kr into Kd 1 minus d initial oxygen deficit minus Kr minus Kd divided by Kd into L0. So, this is how you can find out the value of, this function. I would say you please carry it out in your halls, try to see that this deficit, this differentiation equation you can derive. This can be easily derived, there is no problem. Just you have to transfer t from one place, and finally you will find that in the form of exponential. So again, so integrating that, you will find out the value in the terms of log. So this can be a solution for t. Solution can be solution for t is like this. So the same thing, and as I have said, if you remember, as we have said in the classes, like where we have said, first of all, in cases like this, it's okay, is I think. So here, just so here, as we have said, this is particularly, we can see here, this would be the typical function like this. This is where the function is. So the function, that the typical function that you are finding is the deficit function. D is, this is the D function D that we have known so far, that is the Phillips D is the function, and this is where the Tc is, Tc, this is where is the time, this is where is the deficit, this is where the deficit value, this is where the deficit value, or you can say that this is where the deficit value that one can obtain, and so this is how it would generally go into this Phillips. The first, initially the combined curve that I have shown, it is similar to that curve. It's just similar to that curve. So you can find a plot like this. This one is what is known as the maximum deficit. The maximum deficit would take place here. So this deficit, you can say this is the maximum deficit dm, where would be the maximum deficit would take place. This is nothing but the tangent here, the tangent that you get due to the differentiation itself. So, here this one you would be going to know about all this, and this is how this Phillips-Streeter equation is generally used. See, one important thing about this Phillips-Streeter equation is is of great use. Phillips-Streeter equation is used throughout the world for different purposes. The reason is the advantages of Phillips-Streeter equation is advantages. Number one, it is simple and good for initial estimates. Works well with site specific corrections, Say some cases like site specific corrections would be, say here as we have say instead of L0, if we are instead of L0 we can use a correction we can make as this. Okay, this is the correction that we can make. Say sometimes also in place of initial deficit, if we just see this initial deficit can also be a function can also be used for the initial deficit, like instead of this 3/4. So, this with it gives a basic framework of a function, very importantly, because in many cases you need to start with something. Phillips-Streeter equation gives that start. I mean where you don't know much about the characteristic of the waste, you do not know much about the the other criterias, like the other criterias. In such cases, to start with a Phillips-Streeter equation is perfectly all right, and throughout the world it is accepted. It is very much a very popular form of equation still being used, particularly for modeling of BOD related waste, biochemical wastes or biochemical or even organic wastes, biochemical and organic wastes in particularly in stream, wastes in stream. This is a particularly a quite efficient equation and is used universally people, but it is not certainly does not work. I mean remember this is it says disadvantage is this particular does not work on I mean it is not applicable, does not work on wastes like benzene, tannin, etc. Does not work for like in case of benzene, tannin, etc. right. So, this is where this Phillips-Streeter equation can be used, and this is what it does not work in many cases, as I have said. It is too simplistic at times, but there is no kind of only another important thing is this is where from where the environmental engineering modeling started. Actually, this is where engineering wastewater modeling started. So, that way it's as a starting formula it has a good application, but suddenly with time the characteristic of the waste and all other things have changed. The world itself, the pollutants, different kind of pollutants have changed. Say previously what were the pollutants in water, say in 1950s, has gone considerable change now. If you see the pollutants in the water, so that their degree has changed, their composition has changed, and their variability has changed a lot. So, this equation may not be very good at this present point of time, but for initial estimate it is still very much used, has to be used with caution, but generally for all kind of waste where it is biochemical and organic waste, Phillips-Streeter equation is still very much used, but well, when one is using that, one has to use with caution. Okay. So with this, we have concluded particularly the wastewater in a fixed body of water, wastewater in a fixed system, and as well as where we have considered as wastewater stream. So we will move from this, surface water is closed, surface water is complete, we will move to groundwater on the next class. In the next class, we will start with groundwater modeling. Okay.
(1951), a young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theatres, and from the quiet fibre-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shaped their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring. Where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute, whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire.
आदर्शाय मादर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.